So now we'll get to what I know best, which is lighting techniques. So before we start, I'm going to talk about the relationship between light and an object. Light will come down from a source and it will hit a surface. And there's four things that kind of happen to the light once it hits the surface. It can reflect and bounce off the surface and go in a direction. It can scatter, so it bounces off the surface and reflects in every direction, so it scatters away. It can absorb and change to heat, and then it can transmit and pass through completely unchanged. In most scenarios, you have kind of a combination of this happening. Light will reflect or scatter or do a little bit of both, and might absorb, you can't really see it, might pass through, you can't really see that either. But what we want to do is pay attention to how the light is reflecting off of our samples. So I'll kind of use these reflection techniques as we go through the presentation. I'm going to break up light and talk about what we have into four properties. There's the direction of the light, so how it's coming out from the direction of the wavelength as it's coming out of the light, the machine vision light we have, the wavelength itself, so how long that wavelength is, the amplitude, how tall that wavelength is, and then the polarization is kind of like the direction, but it's like the radial direction of it. Also, there are eight different kinds of really machine vision lights that, if you look at our catalog, it's this thick. There's so many different kinds of lights and different profiles, but really most of them can be broken down into these 8 categories. They just kind of have slight differences between them. So there's ring lights, backlights, bar lights, dome lights, coaxial, low angle, kind of a flat ring light, and a flat dome light. So that kind of encompasses really our whole catalog. It's just different variations of these types of profiles. Okay, so starting with the direction, we talk about bright field and dark field illumination. So when we have light reflecting off of our sample, a direct reflection is where the light shines down, hits our sample, and is reflected away at the same angle at which it hit the sample. So we call that a direct reflection. Versus scattered light is kind of what I talked about at the beginning. The light shines down, and yeah, it scatters out in that direction, but it also scatters out in every direction. So when the light comes down, it's not necessarily just the one and one, it's one and then everything. So when we see that in our machine vision applications, it's important to know which type of light we're capturing. So if I have this image here, which one of these images is the direct reflection in relation to the camera? So what area on this picture is direct reflection? Usually there's more people and I kind of pick on it, but since there's only 4 of you, I won't make you guys answer these unless you want to. Nope, that's direct reflection, exactly. So that light is coming down, it's hitting that sample, and all of that light is going reflected directly into our camera. Versus diffuse reflection is everything else, where that light is coming down, it's reflecting light, we can see it, because if it wasn't reflecting any light, we couldn't see it at all. So it is reflecting some light, it's just not that direct reflection into the camera, it's scattering it, so it's appearing more even and more uniform. So kind of the relationship between direct light and diffuse light, the light angle. So if I have my sample here, and I have a light shining down and a camera shining down, it's a very reflective sample, and I have that direct light, and I have my light shine down, hit my sample, and go up into my camera, I'm capturing all that direct reflection. If I move my light, but I don't move my camera, this light is now going to reflect, and it's not going to enter my camera. It's going to reflect away from it because I changed that angle. So when you're dealing with your direct light, the angle of the light versus the angle of the camera is very important. However, the distance, if I'm capturing all that direct reflection, if I get closer and further away, it's going to get more intense as I get closer, but since you're capturing so much of that light already, it's not going to be that noticeable. So really the distance of your light isn't as critical as the angle of your light. Versus if you have the scattered light that you're capturing, the light shines down, it ends up in any direction anyway. I can put my camera anywhere and still capture the same amount of light in any location, but the closer I get to my sample, the more intense my image is going to get when it bounces off and goes into my camera. So direct light, angle matters, scattered light, distance matters. Really what you need to know. Okay, a few more quiz questions coming up for you guys. Let's say I have this set up and I've got a ring light shining down and a camera looking at the side taking a picture, and this is the picture my camera is taking. If I turn the lights off and turn my light on, I get an image that looks like this. So I kind of, question one, where's the camera? Kind of to explain it, it's shining down, it's off to the side looking. Question two, what happens if I put a mirror underneath that light? What's the mirror gonna look like? Does anyone know? You're right. It shines all the light up because our camera's over here, we're not capturing that light, so it's appearing dark. So, if you were going to look straight down, it would be bright, but we're over here, we're not capturing that light. What happens if I move the mirror to that spot? Correct. That's when you get that direct reflection. So that's where that exact angle of light is shining down and hitting directly at that same angle back up into my camera. So I can see perfectly the mirror reflection of that light. So then what happens if I put paper over the whole table? Before it was a glossy table, had a fair amount of reflection. Now I put diffuse paper over it. How will my image change? It will remove, sorry, I can let you answer if you want. Yeah, exactly. It will remove the hot spot and get more even. It becomes more diffusive. And so kind of a little bit more example of that here. You have a desk that's kind of shiny, kind of bright. You have definitely a hot spot where the light is shining down. In this picture here, light shining down, reflecting up into the camera. But there still is some diffusive moments and diffusive properties around the desk, but it's not an extremely uniform image. Versus a mirror, which is only reflective, you'll see the perfect outline of the light, but you won't see any other light in the outside of that because it's not diffusing any light. And then paper, which is extremely diffusive, the light shines down, it's diffusing everywhere, you get a very uniform image. Why this is important for us to know, essentially, and have to have these ideas, is when I ask you, how reflective is your material? Is it a matte surface? Is it diffusive? I'm asking because I need to know what size of light I'm recommending to you. If you tell me that you have a field of view that's this big and it's a mirror, I have to recommend a light that's about 2 times the field of view, so I can have that angle from the light and match that outer edge of the mirror and reflect into the camera. Typically, that's about twice the size. Versus if your sample's this big, but it's something like paper or really diffusive, I don't have to have a light that's 2 times the field of view. I can have a much smaller light. So knowing how reflective your sample is affects how large of a light you use to get a uniform image across the whole thing. So kind of circling back, we have this is the ring light. What do we call the scattered light and what do we call the direct light? So the direct light is where we saw that ring light image, and then the scattered light is kind of all other light that we see. So how do we use, I just talked about a bunch of reflection properties, like how does that translate to solving applications? And it comes into solving bright field and dark field images. So bright field image is where we're capturing all of that direct reflection, and that's what we want to see to create a bright background and then make the defects appear dark. So what's happening in this image right here is all of this light is reflecting off of this metal sample and going into the camera. But where I have the embossed words, that light isn't reflecting, it's scattering. So less light is reaching the camera, therefore not enough light is reaching the camera, it's appearing dark. So we're highlighting the top surface, but making all the defects appear dark because they're just scattering the light, and we're capturing that direct reflection. The other scenario is if you, instead of capturing that direct light, we move our camera to just capture that shattered light. So now we have that direct light bouncing off our surface and it's missing our camera completely. We're not capturing it, but we're capturing the scattered light from our defects. So those are appearing white while the background appears dark. So when you're solving your applications, you kind of want to think about, I have this defect I want to see. Do I want to capture, is the light scattering off this defect? Is that what I want to capture, or do I want to not see the scattered light and I want to capture the direct reflection light? So that's kind of where I want you to take these principles as I talk to them, is how do I think about it when I solve my applications. Just another example here is another etch boss on metal. If you have the direct flat dome light shining down, you'll have that bright field image because it reflects straight back, but this part scatters. Or if you keep your camera in the same spot but use a different light, you're now reflecting that light away, but you're capturing that scattered light in the camera. Real life examples of when we use this. This is a battery cap. The point was to make sure this little flap here on the battery was folded down. If you were going to solve it with a coaxial light, technically you could find these dark lines, but it wouldn't be as clear as using a low angle light to make sure that that cap was folded down. You can also see a few more defects on the top that the coaxial light will hide. Sometimes both will solve it. You have bright field will solve the application and dark field will solve the application. And how we can decide between the two is important. You know, what do we recommend to our customers? What do we install in our machines? In this scenario, which would you guys recommend, the bright field or the dark field? Okay. That's a great reason. I would agree with that. The other thing that I would say is more important as to why you're still right is the tolerance of the bottle. So this bottle, no bottle's ever going to come through perfectly. They shuffle a little bit as they go down the line. Right here, we are very close to that text. If the bottle's just a little bit closer, that light might not illuminate that L11, and we're going to miss reading that text. But with the dark field image, we have a lot more forgiveness in terms of how close our bottle is placed to that light as it moves down. So if both solutions work, or if you have more than one solution that works, the next step is what fits better into my machine, what's more forgiving in my machine, what is not going to be as intrusive in my machine. That's kind of how we think about it. This is a CCS, presentation, so I'm not going to get into product and all that jazz, but I am going to tell you, what lights do we use to achieve these techniques. So bar lights are always the most flexible. They can be a low angle light, they can be a bright field light, they can kind of be whatever we need them to be in a lot of ways. So for CCS, the direct bar light we have is the LDL2. We also have flood bar lights, which is the FE Flex, and the HLDL3. A little bit on the LDL2 bar light, just so you can kind of know the difference between each one. This is made with bullet type LEDs. They have a wide version and a narrow version available. Two different widths. It can be 16 millimeters and 30 millimeters. These guys are great because they can be really, really small, or they can be up to, I think, 500 millimeters if necessary, and about 30 millimeters long. So they're really good for high precision applications, long story short. The FE Flex 2 bar light is it's a great flood bar light. I don't have one up here. I'm not going to spend too much time on it, but these are great because they're interchangeable. You can take the lens or the cap off, and you can adjust the emitting angle by adjusting the lens. You can adjust the windows, so you can adjust the diffusion, so you can make it more transparent or more diffuse, so kind of right in between, like a standard diffuser. And then it's got a multi-mode driver built in, so you can strobe it, you can overdrive it, and you can just have it continuously on with the adjustable intensity, all within the same light. And they can be made up to 4 meters long if you need it to be. I don't recommend it. It's really hard to ship a 4-meter light, so really we try and do everything we can to talk you out of that option. But if you really need it and you need to pay for shipping for that, it is possible to make a light that long. For the FE Flex, it can be IP67 and IP69K available, and it's made from extruded aluminum, so it's extremely easy to mount. So these are great floodlight options just because they're super flexible. They can wide angle, narrow angle, super uniform, not very uniform, kind of whatever you need. Other products we use to achieve the bright field or dark field is ring lights. So the LDR series has both. The LDR2 is just bright direct angle, and then there's the LA and LA1 are the low angle lights. We have multi-angle ring lights, which are the HPR2 and the HLDR3 and the FE ring as well. A little bit of structure differences between the LDR, LA, and LA1. So the LDR2 is just straight down. It gets your bright field image. The difference between LA and LA1 is the LEDs and the angle that they're at. So the LA has 3 LEDs at a slight angle, so you still get a uniform image, but you also get a little bit of light reflecting off the sample going into the camera. So you're getting the scattered light, but also some direct light, versus the LA1 is what they call a zero degree light. So it's completely parallel to your sample. So you're really just getting an extremely low angle light, and you're just seeing that scattered reflection from your scratch to defect type of thing. The HPR2 is our multi-angle diffuse ring light. This is probably like the bread and butter of a machine vision light, I would almost say. This light's great because it has a lot of flexibility, being multi-angle. It's got a diffusion plate that actually guides the light down based on the working distance. So if you have it really close to the sample, it kind of acts like a low angle light, but as you bring it further away, it acts more like an LDR2, kind of a bright field type of illumination, excuse me. So this one's really, really useful if I'm in a lab and I don't know really where to start. If I want bright field or dark field, I'll kind of just take my ring light, move it up and down, and see what image gets me a better image, and then I go from there with whatever light kind of goes after that. And then the FE ring, this is very similar to Flex in terms of all of its flexibility. Again, you can adjust the lenses so you get a different emitting angle. You can adjust the window so you get either super transparent window or super uniform illumination. It can get polarized or line scan accessories. And then it has auto strobe built in as well, so it goes 700% intensity for the first 2 seconds the light is on. Kind of glossed over this in EpiFlex, it does that too. So in the auto strobe mode, when you plug the light in and give it power, give it 24 volts, the first half a second that it's on, it's at 400% intensity. And then if you strobe it, it will always be overdriving. If you leave the 24 volts on that trigger signal, after that amount of time, it drops down and goes to 100% continuous mode. So you have built-in continuous mode or overdriving all within one light. Very useful. The other way to achieve bright field illumination is a coaxial light. There's LFE3 and the MSU. LFE3 is kind of a standard coaxial light. One cool thing about it is you can take off the a portion of the plate of it, and you can add in diffusers or polarizers or light control that come with the light, so you can kind of adjust how collimated it is. If you add light control, it's more collimated. If you have some glare you want to remove, you can put in a polarizer and use that as well. Or if you need it to be a little bit more diffuse, you can add a diffuser. The MSU is a highly collimated light. I'll talk about collimation in a few slides, but what you need to know about this light is it uses optics to create a more parallel illumination. It's very small field of view, a little finicky to work with. Typically, we don't really need it. It's kind of like when you need it, you need it, but most people don't need it. But that's the different coaxial lights we have. And then for square lights, we have the FPQ3. These guys are kind of similar to the multi-angle ring lights. They have the same kind of light guiding diffusion plate. Cool thing about them is they have a reflection plate you can add to make it kind of more like a dome light or more like a low angle light. But they're great for, honestly, square work pieces. Square light for a square work piece is the idea for that guy.